Hey everybody, welcome back. So in the third part, I was thinking about doing forward simulation of particle systems. So as you remember in the second part, we had this deterministic particle simulation, which means we can go back and forth and it will always produce the same result because all of these modifiers are deterministic modifiers of point positions. And I spent a little bit of time working on a small particle simulation thing that is actually, I would call it forward simulation. So which means it might produce different results, but it might also produce more interesting results. And so I guess this part will revolve about writing some shaders and playing with these effects and see where this is going. So I thought about 2 or 3 things I want to try. So let's make some sketches so we can be on the same base here. So the first thing is that I have this, let's say, this particle simulation, and what it does is it introduces every frame a bunch of particles that are emitted somewhere, so at emit positions. And then we can add forces. So let's say we can add something like maybe we have a surface here, and then we can define forces that attract to this surface. So we can, if this is the center here, then we can basically compute the amount of any force that accelerates all these positions toward the center. And then we can actually do also some kind of reflection. So if there's a particle that crosses through the surface, it can bounce right back. So this could, I think I have some of this already. The problem right now that I have is, quickly visualize how this might look. So let's say we have some points, and then we put this into a particle simulation. And then we draw these points. So right now nothing is happening because we don't have any of these forces. But if we know what is surface force, and if we enable animation, we should see a little bit. Let's also turn on the grid here. Where's the grid? So we see we have a small helper object here so that we can move surface force around, and we already see how okay, like this looks like completely crazy here, but maybe we also should set up some fog so we get some depth here. So basically at every frame we insert these 100 points. And then for each frame, they are being attracted towards the surface there, which is visualized by this little sphere. And if they are reflecting with the surface, then they are being bounced back. And it's already interesting because we can move the surface around and we will have immediately very pleasing, interesting effects that we can later, I hope, tweak towards the soundtrack. And another thing we can also tweak is so at every frame, this bunch of compute shader simulates the particles. And the interesting thing is that it will move the particles with a certain velocity. And so this velocity is defined by this speed thing here, which means we can actually, so if we put the speed to 0, the particle system freezes. The interesting thing is if we do to negative, like the current acceleration will be applied negatively, which also like it's almost like playing the simulation backwards. And with binding this to the soundtrack can also produce already interesting results. So let's try this in kind of interested here how this looks. So let's take the audio reaction. Let's take the output to the level here, and maybe we remap this a little bit to see what kind of range we get there. So let's say, or let's leave it with the default here. And then push this into the speed. So what happens if I play back? Okay. I think this definitely looks broken. I think, where is this? I think it looks broken because we are on the home canvas. And then we should disable this guy here. And I think there seems to be... Yeah, this is, I have to look into this. I think there's also an open issue reported by Sense with this bug. You see some output here. So if the speed is 0, nothing happens. Actually, it's interesting that you see like the rhythmic part, but it would also be interesting to see like this vibrating, like, and I'm not really sure if we would ever, if this would actually be possible to achieve with the current detection thing here. Yeah, it's kind of interesting. So I'm pretty sure that we can probably later dial in this this offset here. Maybe we can have we add a value, and maybe we take let's say we take an animated value and we add some kind of sign to it with like a very high frequency. So maybe this would give us some kind of... This is almost what I had in mind. So like we have a little bit of vibration here, and then we can maybe control it into the... I think it's probably going to be super terrible and annoying to dial this in, but I think we can find some kind of interesting results that will produce something. So yeah, anyways, so this is the basic Part3 system. And so far we have this surface force, which currently, so if we jump into the shader here, look at the source code. then we see that there's a lot of commented code because I'm experimenting with like trying to get it running. But the actual uncommented line is like super little here. And we can clean it up during this video. And so the main thing is we compute the distance. Currently the distance is towards the center, or maybe, okay, like this is. Let's explain a little bit like how this thing works. So the idea is that we saw this sphere thing here, like this thing here. And by moving this around, we can also like scale, for instance, like make it much bigger here, so it reflected earlier. Or by, I think we can actually even like scale it into like something non-uniform, and we can even rotate it. So this works because we take all these transformations and we convert them into a transform matrix. And then the idea is that we, before doing this test, we are actually applying this transformation matrix to move this space. So let's imagine like this sphere being somewhere in the coordinate system. And by applying this transformation matrix, we can move it back into like the unit transform matrix. So that this is X and this is, let's assume this would be Y up. And this would be 1. This would be 1. This would be -1. And this would also be -1. So no matter how much we take these guys and scale and tweak them around, transform matrix after applying this will always result into a coordinate space, to this coordinate system space. And we can check whether or not a point is within the distance of 1, then it's within this surface, in this case, the sphere. So it's probably very confusing explanation, but if you look at the code, so we take the position of the particle and its rotation and its velocity, and then we have this position and volume. We get this by transforming the position, and yeah, if you are confused about why this needs to be a 1, this also still confuses me. So this transform matrix is like a 4x4 matrix, and if you want to transform a position, then you have the fourth coordinate, the W coordinate has to be 1. If you want to only transform a direction, then it has to be 0. But yeah, probably there are a bunch of YouTube videos explaining why you use the one or the other. But in this case, we want to transform a position, so it needs to be 1. And then we transform it, and this is the position and volume. Maybe we even have to divide by W, but no, I think since this is only a field transformation, this should be fine. And then we can take this position and the volume, and if we just compute the length of this, we will get the distance to the surface here. Why do we actually do that? Because don't really remember. I think we do this because if we have like a unit sphere of radius 1, then this complete distance would be 2 or something. So if you want to have a normal radius of 1, you know, like, for instance, like if you have a cube, then we assume the default size of this cube to be 1 unit. And if you would have like a default sphere, it would be somewhat weird if the default sphere with a radius of 1 would be twice the size of this thing. And if you ever used Blender and wondered why the default size of a cube in Blender is like unit 2, which is like super confusing, that's precisely the reason. So they decided to have like, the radius of a default sphere should be 1. That's why a cube should fit into a sphere, or vice versa, like that. So like they should be roughly the same thing. So that's why we bring this down to half the size. What we also do is we use the current velocity to figure out where the position will be next in the next frame. So this is the position here, and this is the current acceleration or the current speed. Then after applying this distance, this will be the next position, and this is what we check to figure out whether or not we are entering a surface here. And if we do this, let's assume this would be the surface here. Then we bounce right back. And if we bounce back, then we use this built-in reflect method. This is built in DirectX. I think it's also available in GLSL, in OpenGL. If we take the current velocity, we take the surface normal. So the surface normal would be always like perpendicular to the surface. In this case, like the surface normal would be that. And reflect would give us this direction here. And then we multiply the result with the bounciness. And if we look at this guy here, so there's a bounciness parameter, and I guess somewhere here, the bounciness. So if we bring this down to lower values, we see that they are accumulating on the surface. If we bring it back above 1, we see that they are getting faster and faster and faster, and eventually they will get like super fast and crazy behaviors here. There are a bunch of issues with this thing. So like one thing is that with the velocity, I think after the reflection, if we reflect, I think we would need to apply this transform matrix again to bring the reflected thing, reflect vector back into like the object space. So I think this eventually needs to be fixed. It looks kind of okay, but I think in the long term this will be an issue. And another thing we want to do is, so currently we have this little method here, but the problem with this is that eventually I want to use not points, but I want to use geometry. So this is actually the nice thing about the system is the result of this is points. So right now we like not these white points, but like points in space with a complete orientation, which means we can also use things like draw mesh points. And then we use, for instance, like a cube mesh or something. I think we should bring the scale down, otherwise the fill rate will be crazy. But if we do this, we immediately get some strange points. We also see that currently all these cubes have the same rotation and the same alignment here. And I mean, it looks actually kind of interesting, so maybe we can do something with this later. But for like a more interesting graphical result, we probably also want to apply the rotation from the acceleration. So okay, let's park that topic. Let's park it somewhere here. So let's make this. Let's say this is our to-do list here. So we have something very little. Or maybe we do it like John Kamek. Oh, can't I do this? Ooh. Or we can. We just cross it out. So so like the on the list later will be by point orientation from velocity. So meaning if we have one point flying that direction and another point flying that direction, and we have a cube, then this cube should be aligned like so. Being a cube here, probably like this guy. So like probably more in the center, and obviously like this guy is being like here. And we can think about whether or not we want to have scaling or something. So we can maybe have a question mark here. Maybe derive point W for scaling from speed. And in my thinking, so like to clarify some terminology here. So this is the velocity. The magnitude of the velocity, like from here to there, is okay, this is the worst level ever. So like this is the velocity and the magnitude is the speed. So the velocity has is a vector of 3 x, y, z, and the speed only has like it's I think it's called a uniform. Okay, then we also have to do, maybe we later apply transform matrix after reflection, and the actual point, so I'm diverging here, but the most important point is, let's come back to this sketch, is currently the reflection is only being handled once the center of the point enters the surface. So if this is the surface here, so then it's being reflected. But what we actually want later, if we have, for instance, a cube or a sphere, then we need some kind of radius, which means if this guy is flying, let's say this is a cube, and let's combine this, and this guy is like flying like then I imagine there to be a radius like here. So like this would be maybe like some kind of like, maybe a computer program we can actually. So let's say we have some kind of estimated radius. Probably the corners of the cube will stick out. And so we don't want to reflect here when the center is hitting the surface, but we want to reflect here. Basically, so this is the surface here. I assume there must be some kind of like earlier distance, and this is probably like the radius. This is supposed to be an R. Okay, so I think this is the most important thing we want to do. Shift reflection distance by radius. So these question mark things, I think we can do this eventually, probably not today. And let's see how quickly we proceed with this. There's one effect I want to try though, and I think I want to try this maybe even before doing the reflection stuff properly. So so currently we have only the surface force here. But I also want to introduce a turbulence. I think maybe I already have this in start, but I'm not really sure. I have to review that. Yeah, like, look at this. It wants to have like an input of a G point, which is not the way the new particle system works. So we want to adjust that. So there's a lot of things we need to work on there. So let's maybe like take off the speed here and maybe decrease the speed a little bit so it's like not too chaotic to look at. Otherwise, probably YouTube will do a lot of funny things with the compression. Yeah, and we want to adjust the turbulence force to work. So adapt turbulence to new particle simulation. And then I want to have the spatial adaptive reconstruction effect. Adaptive. So like, okay, like this is a mouthful. What I thought about, like, so in this situation, we have 100 points and we have 100,000 particles, which means it will give the simulation, what is it, like 1,000 frames for duration, which is like, okay, what's 6 speed crunch for the rescue, which means like 1,000 divided by 6. So this would give us 16 seconds for like one particle to cross for the whole through the simulation here. What I was thinking is if we have if we don't emit particles at all, so let's say we have 1,000 particles and we emit 1,000 points. So this should do nothing. So at every frame, all these particles will be replaced. But if we now say, no, they will not be replaced, but we only emit once. So this is now like a constant animation of like these 1,000 particles, and they will do strange things. I think currently they will bounce a lot because the bounciness is so high. I think what we can then do is, so if we zoom out here, maybe we can go back to the full screen aspect ratio here. So they are like bouncing back there nicely. So they will do their thing here. Obviously later we want to have more particles, but for like discussing this, these should be good enough. What I then want to do is I want to have, so let's say we have, so let's say this is our spatial adaptive adaptive reconstruction. Okay, so and let's pad for the sketch here. So we have these 5 particles, And these 5 particles are our mid particles. And then these particles, let's color them maybe. Okay, let's color them maybe blue or something like this. So these particles are now our simulation particles. So you emitted them once, and then they start to do their stuff. So maybe they move around like, you know, like different, depending on their force, they will do things. So let's say these are all moving there, and maybe we fade out like the original position. So this is where they moved. So, and they start from here. Now they are here. So what the spatial reconstruction effect should do is we will, with the same method that we used here to create the surface thing, we will create a spatial distribution of a value. Let's say we create a square volume. And then in this volume, we can say, okay, are we inside or are we outside of this volume? If we then take this and maybe duplicate it and spread it out a little bit and say, okay, maybe like this volume has a soft edge. And maybe we look from this, so this is a little bit confusing to discuss from the side, but if we say this is a square here, and let's merge this and spread this out, duplicate. So let's say this is completely outside, this is completely inside, and this is the soft edge. Then we can have, we can think about this. Let's make this even like a softer edge. Then we could imagine a value going from 0 to 1 and 0 to 1. So this could be a graph basically, where this is 1, and I guess you could say this is the distance from the surface, and probably with the distance. So I'm not really sure how we spread this. Let's say this is 1 from the distance, the unit distance, and then probably this will be the smoothness S or something like this. So why are we doing this? Because if we have this, then we can move this value, this volume around by changing its center. And then we could say like, okay, every time this particle is within the center, we move this guy back to there. And my hunch is that this will be a super interesting effect. So I'm not really sure, but I think it could be it could look really interesting. So if we push this through, so like this animation would go like crazy all the time, but if we push this volume through once, we are back to this line points. And obviously, if the line points are a more interesting structure than a line, let's say it's coming from points on a sphere or like some radial points or like from a geometry, then this could be a very nice effect. So how far are we into recording? Do you actually see how long the recording is there? Ooh, we are half an hour in. So this is going to be a long video. But at least we now have a to-do list and we have an agenda. So half an hour in, we know what we actually want to do in this video. Yay! We start by adapting the turbulence to the new particle simulation. And we do a little bit of shader coding for that. So let's go back to this guy here. Let's not use the surface force. Let's go back to, let's reset the number of points we have in our point simulation. And then we emit all the time. And currently nothing is happening. And maybe we can also go back to points. Maybe go back to points. And maybe we don't need fog. So here are our points. And nothing is happening because we don't apply any forces to that. And now we want to adjust. We want to have this turbulence force to work just the way the new surface force works. So let's jump in here. So we see how this is being made. Maybe I will switch back to this mode here. It will make things a little bit clearer to see what's going on. So currently we output a point buffer. So this is this guy here. Output. That is the type of the output is a point buffer, and we have an input of a point buffer, which is completely opposite. So it's a linear. So traditionally, what we do with point effects is we have a bunch of points. So let's say we have let's say this is a point in space. No. Wait a second. Let's say we have one point, and this one point has 8 floats. So this is the float for the quaternion. This is the 3 points for the position, and here we have W. Something like this. So like this is pose Y, Z. Make it pretty small. This is W, and this is the quaternion. The rotation. Rotation is 4 components. So this would be a point. So at index 0, and if we have many of these, this would be a point buffer, and this is what we currently passing in. And what all the things are doing, all the point effects, they will take such a buffer, they will create a new buffer and apply their effect. So this would be, for instance, like this would be like a line point. And this, for instance, would be the randomized points. So line points and randomized points. So this would create a buffer of 100 of these positions, and this would create a new buffer, copied these 100 lines into, with just the randomization applied. So with the particle simulation, we don't do this. We take the original simulation buffer and we modify it in place. And the way we do this is by, maybe we can look at the surface force because it does it already. So there is a thing called execute particle update, which is just a means of converting some actions into an output. And you keep wondering, like, witnessing, like, where is this output coming from? And the output is coming from this guy here, get particle components. And this doesn't really return the values. It returns a pointer to these 2 buffers. And this is being provided by the particle simulation. So in here, there is this set particle system. This will generate these 2 buffers, and then it will pass it along to all the forces which can modify these two buffers. So you don't have to understand all of these, but maybe to hear it once, it's interesting if you want to do any particle simulation effects on your own. So okay, so we can't connect this. We can't connect it because we need a correct output. So let's add an output here. Add output, and we take new type is particle system. And this is the particles. And initializes the compiling system. So it takes a while for the first time, but then it's there. Then we can maybe, we can track this out, and it will suggest to us all the operators that deal with particle systems. And we see it's there are only like a bunch of them so far. There will be hopefully some more, but right now we only have surface force, which we already discussed. Turbulence force is the thing we currently do. I think you should not use this because this might be a cycle. So like we are in turbulence force, if we add some of the same kind inside, so that this might be a crash. Hopefully it's not. I think we do cycle check, but I don't want to risk it in the video. And then we have the execute particle update, which we talked earlier. And then we can basically say, yeah, okay, this is the thing we want to update here, and we don't need this output anymore. So we can just throw it away. If we go out, this should allow us to connect this to this. Yes, because this connection matches. So let's move back in and think about what we want to do here. The first thing is that we don't need any inputs whatsoever. So this can go away because the input is coming from the particle system. And to get that, we use get particle components. And it tells us, wait a second, they are not attached. They are not attached because this guy is not connected to anything. But this gives us 3 outputs: the points, the simulation points, and the length. So the length, this is the number of items in these 2 buffers. And we can use this to calculate the dispatch count. And if you ever wonder what the dispatch count is, so this shader, apply turbulence, here's the shader. If we take a look at the shader is being computed in parallel 64 times. Which means to process, let's say, 100 particles, it has to run 2 times. And this is the dispatch count. So, the first dispatch is run full with 64 parallel, and the next dispatch is also going to run full, but some of these will be discarded. So then we have to, the actual compute chamber is down here. And currently, wait a second, why is this actually, why does it have 2 compute shaders here? We have a grid point. Okay, like the turbulence force was a little bit special because it has this visualization thing where I earlier tried to visualize the distribution of the field by point arrows. And that's why I ran this twice, once with a grid points field and once with the actual particle simulation. I think let's ignore this for now because it mostly involves the visualization of the gizmo. So let's maybe just call this gizmo visualization for now and like ignore this completely. we also have this has time change parameter here. And I think, yeah, it's already did advanced with motion blur. We only want to execute our compute shader if the time advanced. So if the simulation is paused, we can actually skip the execution. Yeah, I think this will be better. So then, so we did with the count output. Now, like UAV stands for Unified Access View, uniform, unordered access view, which means this is a shader view that allows a compute shader to read in any of these positions here. So like it's unordered, so it doesn't, like normally you have like this ordered view, which is of course much faster, but unordered access view allows us to read and write at any position we want to. Actually, right now we don't really need this because we don't have particle interdependencies. But yeah, actually, maybe there's some potential for optimization here. But anyways, let's go back here. We take these and these unordered access view. If we drag them out, we see that the only thing blinking in the whole graph is like this and this, the two compute shaders. And so we, if you hover over here, we see that there's the UAV array, and we can drag this in here. And the order must match. And then we can check our shader again, and we see that there's a point here. Let's call these points. And it's attached for the first index. And we want to have two buffers. So let's call this SimPoint. And these, let's rename all these two points. And let's call this guy SimPoints. And this goes into second uniform access. And we can see that the shader is actually not crazy complex. So we have a bunch of commented code down there. And besides this, it nicely fits on one page. So let's quickly go through this. So we remembered earlier where I said that we had this calculate dispatch count, and for 100, make a small sketch. So let's say we have 100. No, we had a sketch here vertically rewind. So if we have 100 entries, so let's make it like, let's assume, like this would be this stack. Then it's 100. And each of these entries is like one of these. Actually, we have two of them because there's the points here. And there's the SimPoints. And the SimPoints holds additional information like the acceleration and velocity and radius and stuff like that. So anyways, if our thread counts was 64, and 64 is a little bit more than half, then if we have two draw calls here, then it could be that we have some passes that exceed the actual number of elements. And so what's going to happen if we have this index of larger than 100 or exceeding the number of elements in the buffer? As far as I know, that's undefined. And what I learned is that we have to have this guy here. So this operation, let's increase the font size a little bit. So we take the number of structs. This is a let's call this point count. It's a little bit easier to read, and we don't care for this dwight. So let's rename this to something undefined. So we take the point count, we use the built-in get dimension functions to figure out like how many points do we actually have. And then if the index of the point we are currently processing exceeds the point count, then we do nothing. So this is what this starts. So if this exceeds the number of points we have, so if we access point number 110, like, oh, there's no point 110, we should do nothing. So this is what this does. Okay, then we have this guy here. So this is the actual index of the operation. So I think some people call it like GI, group index. Yeah, I just call it I. And the only component we need for that is the X, because we have a one-dimensional array. So we take the variation offset. We have this hash function here, which takes an index and it will return a random value, and then we can increase the number of variation by this parameter. So this is just a random offset we apply to the position of every index before we process the noise field. Then we take the position. So points, position, what, like, I don't even know, like, so obviously there seems to be some kind of like weird glitch in the noise function we are using. Let's leave it with this. Then we have the actual noise lookup. We take the position, we take the variation offset, we take the phase of the noise. So there's a phase parameter here which will animate the noise. We have the frequency, which probably is the scaling of the noise. And this is the actual position within the noise field that we are looking at. Then we are using the actual predefined function. I think it's being in one of these. Can I click here? Can I click here? So don't ask me what this is doing, but obviously it's doing a simplex noise, and a simplex noise is something by Ken Perlin, does some kind of Perlin noise. Curl noise, again, so many divergent, but it's like, so if you have a field here, so this is X, this is Y, and for now let's ignore like the depth dimension here. And every position in this coordinate system returns a direction. So this may be there, and this may be there, and this may be there. You know, this is the offset, that is the result of this noise thing here. If we do this for Perlin noise, and this, you know, you can imagine maybe, let's take another color here. So if you connect these things, you can almost think about this like a landscape, you know, like it could be like the height lines of a mountain, where like the direction, let's say, is always flowing down. The problem with this is that you will end up with regions that are at the bottom. You know, you can imagine like a landscape looking like this. Like this would be like a landscape here, and so the result of this guy like here would fly there, and this guy would flow there, and this guy would flow there, and this guy would flow there, and so on. The problem is that you see that we have this sinks, and eventually all the particles will gather in these holes, and none of the particles will be up there. And this is bad because it will just look poor. You know, it will, or sometimes it might look interesting, but in many scenarios, this will lead to unwanted particle concentrations. And that's why you have curl noise, and as far as I imagined curl noise, I think it will try to somehow mitigate the situation by moving, returning, maybe something like so, but I'm not really sure. I think it's more complex than just like flipping it by the cross vector or something like this, a cross product. I think it's doing something clever, but it will like lead to nice curly fluid-like simulations that will keep the concentration homogeneous. So it will try to avoid density concentration in these things or lack of any particles in these hilly regions. So anyways, a detour here. So we, if we're using this curl noise parameter, we're using this. And so whenever possible, we try to avoid if-then blocks because I think this is a little bit faster in shader. All of this, I guess, like super performance critical people would say like this is like insanely, it would be much better to have like if then and not use parameters. But I think if the parameters are constant, I think it will not make much of a difference in the performance. So anyways, we are also getting the rotation. We are normalizing the rotation, and then we have these really weird attempts here of getting the acceleration from the quaternion. So this was an ill-fated attempt of mine, and this is complete bullshit. So we don't need this. We don't need this. We only want to get the acceleration and the acceleration, or the velocity vector 3 velocity, and it's stored in SimPoints velocity. For some reason, I'm thinking about moving to capital letters. It's extra confusing. Then we take the current velocity and we add the result from the noise offset up there. And that's all we do. So we don't need this, and we don't apply this to the rotation. So like no matter how this is moving, the rotation will always stay the same, and you will remember we had a to-do list for that. Okay, let's go back here. So back to our source code. So we only take the velocity, we add the velocity, we apply the noise to that, and we don't store that. We only store SimPoints, or actually, what do you think about it? If we only apply this new noise offset, we don't even have to fetch this into a variable. We can just add this there, noise. And we don't need all this. And now to make it, it might not be more readable, but I think it's easier to write it like so. So the only thing it does is, to summarize, we take a random offset, we take the position from the of the points, we use the position and the variation offset to actually find the position in our noise field here. And then we take the result of this noise and add it to our velocity. This is how we do. I think if we compile this, let's see if this, let's split this thing here. So if we compile this, let's remove all this commented code. We don't need this anymore. If I press save here, we see an update up here, down there. So it was compiled successfully. And there you go. It's not working, but it should So let's see what's happening if we take the draw points here. If we pin this here, if we double click here, we see that, you remember there was a warning here that we don't get any outputs, and we see that this is being updated. I think these are updated implicitly, and this is being updated. And the whole gizmo thing, let's disconnect this for now, we don't need. And actually I think something is already happening there. So let's maybe increase the amount. Yeah, and there we go. So some kind of like stuff is happening there. Maybe we apply the fog again. So like there, yeah, some kind of like force is happening there. And I think if we now, for instance, like increase the frequency, we should see more other things happening. And if we increase, for instance, the variation, we see how these are moving in a random fashion. I think if we change the phase, we should see how this noise feed is being animated. Nice. So good job, everybody. Let's go to our to-do list. So we did this. And like what's the hotkey here? Okay. It's like, how can I? Isn't there like a hotkey to strike it through? Strike through. Oh, no hotkey. Okay, then now we want to do the spatial adaptive reconstruction effect. It's although it's not really related to the simulation, because it's not like a form of forward simulation. It needs to be implemented as some kind of force, because it needs to be inside the modifiers of this particle simulation. So and let's build this from scratch. So the idea would be, once again, we have so let's say our idea was to have a bunch of points. So let's make it radial points. Let's say we have like 1,000 or 10,000 points, so we can actually see something. And we have only 10,000 points in our simulation. And we only emit once. And then we want to swipe our volume through this thing and reconstruct the circle. So this is our aim. So how do we do this? I think we just duplicate this guy here, because it has all the transformation stuff, and then we can adapt it. So we right click, we go to symbol definition, we duplicate as new type, and we call this guy I mean, we can always rename it later, but thinking quickly would be, we can blend 2 points. Blend simulation 2 points. Blend force, reconstructive force. Yeah, I hit this thing every time I'm like all these operators. Maybe there could be a convention of having this force suffix, but like it's not really a reconstructive force. Let's call it reconstructive force. How did we what did we call it in the spatial adaptive reconstruction? I think reconstructive force is okay. And then stores, yeah, blends the, maybe it can be, so currently we blend the, so this is a good question. So let's together think about this. So there are two ways of doing this. So let's make a sketch here again. So let's say we have we had this sketch here. So let's take this guy and make it big. Let's say like we have this guy here. So this is the current position, and this is the position of the original point. So if this effect is working with full force, this thing should end up there. So now we have two methods of doing this. The one method could be we take this actual position of this point and move it up there. So we move the position. The other method would be, no, we apply an acceleration towards the target point and use this. The first might be more predictable. The latter might be more interesting. It might yield more interesting results because we can then control it also with the simulation speed parameter. Interesting. Let's start simple and just I think we should just blend the position and the rotation towards the original. Blends the simulation particle point towards the original matching emit points. Note the effect is likely to produce predictable results if the number of emit points does not match the number of simulation points. So unpredictable doesn't necessarily mean bad. It just means probably not what you expected or hard to plan for. So let's have both. So we have the turbulence force, but we also have the reconstructed force. So let's commit this. Since this is the same thing as the surface force, we have all the same parameters. We have our documentation down there. And now we can go into adapting all these parameters and the shader. We double click on there. We pick the shader. This is still the original shader, so we definitely don't want to modify that shader. So let's go in here and save this. Let's use the hotkey Ctrl+Shift+S to save it somewhere, and we save this as reconstructive force. And so obviously we have the like this is so this really needs some cleanup. So like this, the naming convention is all over the place. I think we had the prefix sim to put it into the simulation category here. Yeah, this is bad. It really needs some cleanup. Okay, anyways, let's save it like so. And then obviously we only saved it here in Visual Studio Code, so we also have to apply it here. So let's go in here and sim reconstructive force. And let's see what else we have to do. So like the first thing that we notice is, wait a second, we get these particle components, and this is the current, the current buffer of like the position or rotation, and the current buffer of let's say this is the particle points. And this is the it would be interesting to clarify this. So this is the points, and this is the SimPoints, and the SimPoints has the only important thing for now is the velocity. It also has a radius, which we might deal with later, and these together are the particle simulation. So we have these two buffers here. So obviously, these always come in a pair. Here these are these two buffers, but we don't have the target position we actually want to blend to, which makes it kind of funny. So I think we probably need a connection of this guy into here. So let's add that. Right click, we add input parameter, and we call this buffer with views. So this is the type we need, and these are the target points. Add, click, and we take this. I think there should be get buffer components, I think, and we need only the shader resource view. So the difference is the unordered access view allows us to write into that buffer, but we don't want to write in there. And as far as I know, the shader resource view is a little bit faster, allows better caching. Once again, if I drag this out and at the same time scroll with the right mouse button and can zoom around, like the only thing highlighted is this shader resource view parameter of the computer stage. So let's connect this here. And we need to access that. To be honest, I always forget the correct application, how this is supposed to look. So we take, for instance, like this randomized points, double click in here, we select this guy, we click on edit, and this is how we access that. So let's go back to the apply sim constructive force and add this guy here. And for the uniform access, we need the U prefix, and for the SRV, we need the T prefix. I don't know why this is actually. And also keep in mind that this order also plays a role. So yeah, I think this is kind of funny that this definition in here. So this would be the target points. And the format or like the type would be a point. Okay, then we have all this stuff down here, which is bad. I think this comes from the original select point shader. And I think we probably want to use that later or now. Excellent question. Let's start with something simple. Let's start with a circular radial structure, and then ignore the sign distance functions in here. So we can always make it more complex, or I can make it more complex without a video call. Like, I think this will be more confusing. So I think we want to have this guy in here. We don't need that for now. We take the position and the velocity. So, to be frank, I'm not really sure what to do with the velocity. I guess we could argue that the mid positions don't have a velocity. It's not quite true because the particle simulation, this has a parameter here to set the initial velocity from the orientation of the points. So you can say initially they are not still, but they are maybe probably easier to just show you what's going on there. So if we go back to if we emit these guys and we say we only emit like 100, and we leave the, make this a little bit bigger. So like this is how they are being accelerated from their original radial position. And if we would look at these guys here, visualize points, we see that there is an orientation here. So maybe if we increase the axis here. So this is the orientation of the radial points. And initially they point with the X outwards and with the Z towards the camera, which I'm still not really sure whether this is a good good constellation or not. We also see that the radial points per default has like this closed line attribute. So this is important if you want to draw like a line circle, but for us, like we don't need this overlap over there, so we could disable this parameter. So anyways, Z is defined as forward, which means if we go, and maybe group these together here. Let's make a group and let's pipe these two guys in there. So it's a little bit hard to see, but these are the midpoints, and this orientation of the points is completely ignored. But if we then say set initial velocity, we see that they are changing a little bit. And if we now increase the initial velocity, we can see how these are being forced out towards the z-axis. And yeah, obviously this can be super useful for like a bunch of effects. So yeah, in a long time, we might want to play with that. So, and yeah, back to the back from the tangent. So yes, these they can have a velocity depending on the parameter in this, but we don't have the initial velocity parameter inside in here, which makes it kind of cumbersome. But I think in the long term, not only in the long term, I think very quickly we want to add this and this parameter to the particle simulation buffer, because this is yeah, this will be required later. Okay, anyways, I was completely off track here. So let's back to the reconstruction force. So we want to take the position, the rotation, and the velocity of the current particle. Then we want to compute the position inside the current volume. We don't need to look forward, so the current position is good enough. And then we can take the current position to find, so first, if you remember, we go back. The first thing is we transform the global distorted space into the uniform space that goes from 1 to -1. This is this guy here. And then we take the distance inside this position, which gives us a proportion from -1, from 0 to 1. And then we can basically apply this. So let's comment this out. And maybe also let's clean this thing. Make it a little bit more readable. So I don't know why we need a force here. So go away, everything just go away. So so what we want to do is, depending on this value, we want to reconstruct the original emit position. And this reconstruction is basically just a lerping, which means we can take the point at the current index and set the position to, obviously an S is missing, a blended value between the current position and the target position. And the target position would be, so now it's getting, we need some kind of index here. And the problem with the index for the target points is that we can't assure that the length is the same. And I think the easiest thing would be we take the target points, get dimensions, num. Oh, let's talk this like a horrible. This is the point count. And let's call this sim point count. And let's have an emit point count parameter up there. And here this will be the emit point count and this divide. And then we can compute the index for the emit particle by saying we take the emit point index equals the overall simulation particle index, and we modulo it with the emit point count. So this will ensure that if we have 100 points for the simulation and we have 10 points for the emit points, this is maybe like a 10 here, then this guy will be repeated 10 times because it will fill up the structure here. So with the points, we have the velocity in there, and we take the index, and then we blend to the emit points equals emit point index dot position with the, and maybe we call this not distance but blend amount or blend factor. I really like the I like to use the suffix factor if I know that it goes from 0 to 1, roughly. Blend vector. Obviously the midpoints. We called it here target points. Let's go target points. And then we can take everywhere, like this guy, we call it target point count, and this guy we also call target point index. And so blending, like lerp, I don't know why it's called lerp, but this is the short form for linear interpolation, which means if it's 0, it will take the original position. If it's 1, it will fully take the target position. And we do the same thing for the rotation as well. So rotation, and sadly we can't blend the rotation because or we can't just lerp it. We have to use a function called qslurp for that, and don't get me started on that one. So qslurp, target points, this is the rotation, and this is also the blend factor. And I think we should also, for now, restore the velocity. And this guy we can use lerp again, and we take the original velocity and the target point velocity. There is no target point velocity, we had this earlier. So let's take, let's say just 0. So we freeze them if they are fully restored. And that's all we have to do. So not too complex of a shader here. I'm so curious. I'm so curious what's going to happen now. So the first thing is we should also add some kind of visualization what we're actually doing here, because it will be super hard to figure this out without any gizmos. And so let's go into the reconstructive force and see if we have a visualization here for like a gizmo. And it looks very, maybe we can go back to this other mode. I think it will be easier to read. So let's put this in the background, switch to focus mode here. And maybe we increase the, like this, like the shadow here. So I think we don't need the axis, but maybe it's kind of useful to have like the axis there, but maybe it's a little bit big. So let's reduce the size here. And we see that currently everything is concentrated at this inner sphere, and I'm kind of I think this is kind of peculiar. So if we move this, what's even happening? Wait a second. We wanted to have a fixed number of midpoints, which should, for the start, match the number of simulation points. Like, what? What's happening there? So if you move this guy around, so maybe we don't need. We only want to have like the original points there. So let's discuss what would have been the expected behavior. So I would have said that if I move this circle into like if I move the sphere, maybe we can increase the color of the sphere here. Sphere gizmo, and let's make it like a little bit brighter. So my expectation would have been if I move this, all the points inside the sphere should restore towards the circle position. And to make this a little bit easier to understand, so we had this visualized point here, and then maybe we say, okay, like the orange points here, and maybe we don't need 1,000. Maybe let's start with 100, so we can distinguish the different points. And maybe we don't use turbulence, because turbulence is a very difficult thing to follow. Maybe we use the directional force. And we don't need the gizmo for now. Off. And maybe we, to see a little bit easier what's going on, we can also have an animated value here. And the animated value has a second output was hit, and we can say, okay, every time this is being restored, we emit the new points to see a little bit better what's going to happen. So let's make this like very slow. So we see that if we disable this guy, the points are being moved up. So they are being accelerated towards the top, which is what you would expect from the directional force. Maybe we don't use up, maybe we use forward. It's maybe easier to follow. Okay, so they are being accelerated towards the default camera position. And if we now enable our reconstruction force, something, we can see that they are being accelerated towards zero. And for some reason, the position of the sphere is being almost, no, it has like what? What's even going on? What? Interesting with it. So let's look at the source code again. We have the points, we take the rotation, and so let's first check whether our distance operation here works. And we can do this by just, for instance, we can write the distance towards yeah, this is a nice hack. I think you will hate this. So we have the blend factor here, and we take the points, and we take the current index, and we write into the W parameter something. So if you write there a value, we can see that currently this is being used for the size of the points. The nice thing is we can also enable this new show indices thing here. And there is a connected table. If we enable this as well, we see this is the current value for each of these, okay, like the first 31 points. And then we can go in here and say, okay, if we don't write it to 1, make this over here. But if you move it to half or so, oh, I would have expected this to make a difference. But it doesn't, because we are not using we are visualizing the original points, but we know we want to visualize the actual simulation points. So like put like so. And now if we write this 2, we see, okay, the new values of these is 2. And if we write the distance, we should, the blend factor, we call it blend factor. Okay, we see that something is happening. Maybe don't do anything else. So we and we see that obviously it has the opposite effect. The further it gets away from the sphere, the higher the value gets, which is obviously true, because we are using the length vector. I think we should have inverted this guy. So if we we should also, so we see that now it's negative, which is like even worse. But I think if we first clamp this to 0, from 0 to 1, so let's make this saturate. And if you ever wonder, saturate is identical to clamp 0, 1. I think, saturate might not be defined with HLSL, but I think I got used to that eventually. So, okay. So now it starts with some distance and then it goes into 0, which is the effect we want. So now if we uncomment this. So now everything gets pulled into 0, which is, okay, this is definitely wrong. We can look into this. Maybe we ignore like this whole velocity thing for now. Which means that the target position is 0, which is, might be, yeah, obviously it's true because it is 0, because we don't have our radial points connected to our reconstruction force. So let's do this here. It's a target. Yeah, seems to be almost doing what we expected. And now if we move this away, so yeah, look at that. So these are simulated. And if I move this, we can reconstruct the original thing. So the, I think the size of our gizmo is still like a little bit broken, but the idea seems to be legit. So let's try this with some turbulence. So it's, and we, for now, we don't need this anymore. So, okay, it's moving and it's being held there. And if we, let's clean this up. This looks like very confusing here. Let's move these guys here. I think it makes it much easier if we have some space here. So, let's get rid of this. And we don't need this anymore. So what do we have here? We have radial points. We emit these radial points once. And then we add some kind of turbulence force, which moves these guys like around. If I without the, yeah, the turbulence force seems to be very, yeah, it's a huge force. So let's start from scratch here. So maybe we have a little bit less. So. And if we have this turbulence center, we can move this around to reconstruct the original sphere. And obviously we can now go into like different shapes of maybe only have the shape being active outside or inside, so we can invert the distance functions there or do other interesting things. But I'm pretty happy with this result. So maybe we can also reset the velocity if it's in there. This might also might clean it up even more. And another thing we should eventually add is to support gizmos, so we can track this center of the reconstructed force with some kind of gizmo in there. You can even like interesting. So we emitted it once, but we can change the position of the reconstructed points, which is also kind of interesting. Yeah, I think I will need a break now, but we made some headway. So before I make a break here, so we have partial progress on this one. So and I think after the break we can try to make this build something with that. Okay, see you in the next video.